Um, so I have the pleasure today to introduce Ming Wang, who is an assistant professor at University of California, Riverside. So he's joining us from the West Coast of the United States. So he got up early, much earlier than Ming typically gets up, I would say. So he could be here today. We've been using a lot of the tools that Ming has developed extensively in this workshop. So you've heard of GNPS multiple times, used it. So Ming gets all the credit and also a little bit of the blame for any of the things that are maybe less than perfect. But Ming is very responsive, very engaged in the community. And I'm really excited to see what he has to talk about today. So with that, Ming, take it away.
Thank you, Alan. And, thanks everybody for, stopping by the summer school. Hopefully you're enjoying it. I didn't realize it was going to be such a star-studded staff. So I'm a little bit jealous that I couldn't be there in person. So anyway, thank you for the organizers for having me. And thank you all for just being here and sharing your time with me. As Alan said, I'm a new faculty at UC Riverside here in Southern California. We just got past the hurricane, so everything's good. But yeah, I'm excited to tell you about a little bit of some new tools, some things that I'm just optimistic about coming out of my lab and collaborators for the future. And as Alan mentioned, a lot of the tools I helped work on over the years, and I deserve the blame, but really it's been a community effort with about almost everybody you see in front of you at the table and a lot of people in the audience as well. It's really been an amazing journey to build these tools, find out what people need, and just make it work all together over the years. So I'm eternally grateful for all the friends and collaborators over the last decade and a half of doing all this. But without further ado, I want to get started with some things I want to share with you all. My talk is called Community Scale Tools for Metabolomics Analysis. And you guys are going to be experts after the summer school. No thanks to me, but thanks to everybody else. But just to share some new ideas and new tools with you all that we've been working on. So here are my disclosures. And one of the things behind the kind of a high-level thought process of GNPS is it's a combination of multiple things, right? So we have tools and algorithms, visualizations that you all interacted with, that you played with to analyze some data. But in conjunction with that, we also have a data repository at GNPS that includes published data and resources from the community. And so today it's a little over 50-60 terabytes of raw metabolomics data and about 1 billion tandem mass spectrum. So a decent size, something you don't want to be really downloading on your own personal computer, that frequently. But then at the other end, we also have knowledge bases, which is community aggregated data where anybody can contribute to and then everybody can leverage. So examples of this are spectral libraries, which have MSMS and the structure, so you can re-identify known compounds and see what other people have identified in their data. So it's these three things working in concert that we think really makes things a lot more valuable. And those are all accessible via the web at GNPS. And so just giving a historic bent to this, we started this whole endeavor about 2013. I remember I was a grad student at the time, and Christmas break was amazing for productivity. Didn't go home. I just stayed in the lab. Don't encourage this awful work-life balance, but that's what I did. And then we launched GNPS early in 2014, and it's grown from there. And so just as a kind of a recap, over the last 7, 8, 9 years, we have this chart here showing the number of jobs that we run every month. So bottom line, it's growing. The community has come and analyzed over 600,000 jobs. It totals about 25 million LCMS runs. So, it's something. So, we're very excited about that. So we've had a pretty good run. So GNPS is one thing that I've been very excited about. Another thing that I've been excited about very recently, I just want to share with you all, is the arrival of my first son, or my son. We'll see in a second. And it's been amazing. This has happened in July. But one of the things that I realized, maybe it's obvious, but I'm a computer guy, and computers are more predictable, is that there's no off button with a baby. When he starts crying, they keep crying, and you can't just ignore them. So, which has been amazing as a parent. But the one thing that has caused some issues is that whenever there's a server problem or some fault or some software bug, for example with GNPS, I'm a little preoccupied. So and we don't have a particularly big staff in doing maintenance and upkeep. And so what we've noticed, especially during July, right as my son was born, is that there were a few issues, a few bugs that caused about a 9% downtime over in July. And so that's about 3 days where the servers are down. And so not great. I got dozens of emails, and then it disrupts a resource that people rely on for their work. So I feel pretty bad about something like this. So this made it evident that there's a clear need for resiliency, and you kind of notice it. And I got a text from Danny at like 1 a.m. here saying, "Hey, I think we killed it." So you guys all got a little taste of when a centralized resource goes down, it's not great. It's hard to proceed. And so currently GNPS is all these pieces of GNPS are housed at UC San Diego. And so I did my PhD and postdoc work there, and working with Nuno Bandera and Peter Dorstein. But it's a single point of failure for the community, and it's not great. There's other downsides to it, but it's also just not great. In case there's maintenance, people can't get their work done. And so we try our best to have uptime and availability, but we are not, Amazon, Google, or Microsoft. So one of the things that we've launched at UC Riverside is something that we creatively call GNPS2. So with a lot of the big data, it's going to stay at UCSD. A lot of the knowledge bases are going to stay at UCSD, but a lot of the tools will be rehosted and kind of remixed in GNPS2 at UC Riverside. And so what does this buy us, right? At the end of the day, what's kind of our overarching philosophy for this is, number one, as I've alluded to, is resiliency. So if you have a problem if we have a problem at UCSD or we're undergoing maintenance, we are able to redeploy all the tools web accessible for anybody to use on commodity hardware at any institution. So we'll have backups. That's great. Number two, and these are kind of in difference from GNPS1 that we really didn't like, is that it allows us to have flexibility. Because it can only run at UCSD, it can only run literally on a single computational cluster at UCSD. It was just a nightmare to do any sort of development, or if anybody wanted to run the tools on their own computer, on their own data, whenever our servers were not enough, it just was not possible. And so we want these workflows to run anywhere, not just at UC Riverside servers, but anybody who has a Linux-ish machine should be able to do this. And so this allows us to also make workflow development for GNPS2 significantly easier. And so just as an FYI, you don't need to be an employee of UCSD in order to do this anymore. It enables, we hope that it facilitates more shareability. And so we can access public data from not just UCSD resources, but from any public mass spec repository from anywhere in the world, from metabolomics, proteomics, glycomics, things like that. And also, if we have multiple versions of GNPS2 running, we can easily push results from one server to the other and share it amongst the community, again, for more resiliency. And kind of the final point is privacy. And so one of the things that you all are kind of the institute that you guys are at right now is a serum from real people, right? Babies. And that cannot leave, that raw data cannot leave that particular institution. It's private. So uploading it to a resource that you do not control, probably not the best idea, and is probably a violation of your privacy mandates. So with GNPS2, we hope that institutions that want to use the tools that we develop, they can use it by deploying it internally, and they can maintain privacy of their data. So that's kind of one of the advances that we have here. And so those are the kind of the key things to be gained from this new platform. So GNPS2 at UCR is live today. It's in a beta. So if you'd like to try it, reach out. We can make you an account. Again, we have very modest resources in a new lab, my new lab there, but happy to share with the community in that respect. And kind of looking forward in the middle to near term is we're hoping to bring online other instances of GNPS2 around the world, some in Europe, some in South America. These are kind of our biggest users of GNPS. So we'll see how that goes. And so then if I'm asleep, there will be some instance that's running around the world. You don't have, if something breaks, you don't have to rely on me. So that's both freeing and kind of exciting for me. But okay, so that's enough about kind of the infrastructure kind of components and kind of democratizing these tools out into the world. I just wanted to mention a few, talk a little bit about a few tools that we've been working on in GNPS2 that specifically involve big data. I think that it's a pretty exciting aspect of our work. And how can we start taking advantage of all this data that only recently people started depositing? And just giving you a point of reference about when I was starting my PhD, there was almost no public small molecule mass spectrometry data available. People just didn't release it. And now that we're making utility from the resources, and the culture is changing within the community, we have thousands and thousands of public data sets available, and at least dozens to hundreds being released every month across all the public repositories. So it's definitely very exciting times, and you can see kind of this accelerating growth, at least at GNPS over the past couple of years. So pretty exciting. But at this kind of scale, what the heck are we supposed to do with it, right? So again, 60 terabytes is not huge, but for somebody to download it and work with it and kind of extract some meaning, it's not the most straightforward thing to do. And so just to create an analogy for what other people expect in adjacent fields, within the sequencing community, it is expected that you're able to easily go to NCBI, look at all the deposited genomes and sequences, and ask the question, hey, where else has somebody seen this particular DNA sequence ever? Whether it's across published finished genomes or even in the short read archive of raw reads, right? This is a question that that people take for granted within that particular area of bioinformatics. And so we kind of ask the question, why can't we do this for mass spectrometry? That we can do a similar thing, and it's a very natural, and we hope that it's a very useful question to be able to answer. And so one of the tools that we created is called the mass spectrometry tool. So MAST for short, kind of a clever acronym, or kind of clever name there. And in the same way with BLAST, where you can take a DNA sequence and search it across all NCBI, go into some server and do this procedure, we want to be able to enable the same thing for tandem mass spectrometry with MAST. And so the analogy here is that instead of looking for a sequence, our kind of fingerprint or barcode that we're actually looking for is the whole tandem mass spectrum. And then what we can do is we can go to all the data sets and all the data that's ever been published before. We do some clever indexing on this data and pre-processing so that we can start doing the comparison and answer the question, in what context, in what data sets, in what kind of metadata have we ever seen the molecule that you're looking for, right? And so as you guys have seen, when you run these untargeted metabolomics experiments, you end up with thousands to tens of thousands, and depending on the scale, maybe hundreds of thousands of analytes in your data. The vast majority of them are unidentified to known structures. So you probably want to get a little bit more context before you get the structure out, right? So where else has it occurred? In what kinds of systems does it occur? And what kinds of experimental conditions or diseases and things like that does it occur? And just so walking you through one particular example, when we published this original work a few years ago, there was one particular tandem mass spectrum that we studied in a human data set. This happened to be human stool. We didn't know what the actual molecule was at the time, but what we did know was that it was overexpressed in patients that had non-alcoholic fatty liver disease as compared to healthy patients. So this is something we detected in the stool. But again, we didn't know what the structure was, and we kind of said, well, this is kind of interesting, right? This is a kind of an interesting finding that it's upregulated or higher abundance, relative abundance in non-alcoholic fatty liver. So, but we're like, well, could it be some sort of artifact in our particular analysis? Could we find another context and other studies where the same molecule was being, which we observed, that would give us a little bit more information and corroboration of our finding? We did, but took the MSMS for that particular molecule, again, that we didn't know. We used mass to search all public data. And what we observed was that the same analyte was found in 43 other data sets, right? So a decent amount that was found elsewhere. And we were able to kind of confirm that to at least, a first approximation, it was the same or very similar analyte that we can see here on this mirror plot. And so that's fine. 43 is quite a lot. As we're digging through these 43 data sets, we found some that had detailed experimental data. They told us, hey, for example, there was a mouse study that half of the samples were from mice that were fed a normal diet, so expressed here as NC, and then another half was fed a high-fat diet. So not great for the liver health, but for the same exact metabolite, we went back in that we found with mass, and we looked at the relative abundances. And one of the things that we observed was that this same metabolite was observed in the stool of the mice and was higher in the high-fat diet versus the normal food. So this gave us a little bit more confidence that this particular molecule that we didn't know seemed to be corroborated by another mouse study and kind of similar, not the same experimental setup, but kind of a reasonably analogous experimental setup. So we think it's something involved with the liver. So that gave us a little more confidence in our particular hypothesis. And then some collaborators actually was done with Peter's group, did the discovery work, and they solved the structure and they hypothesized that it was actually being synthesized by the microbiome in the gut, and it has some implications on liver health. So it was the bile acids is involved in that direction. But the bottom line is we started with a hypothesis in our own data, and we were able to gain a little bit more context and corroboration even before we could identify what the molecule was by leveraging all this public data that was available. So again, this won't be perfect for all situations because there's differences in how people run mass spectrometers. You might not find the same molecule in others if you're tuning your mass spectrometer in a unique way. But if we're all getting to a place where our tandem mass spectra are tuned reasonably similarly, this might be an avenue to kind of explore. Okay, so we're able, that's one example. There's hundreds of examples now of people applying this using this tool. But the most basic intrinsic operation that we have to do in order for mass to work is we have a single tandem mass spectra, for example, here on the left, and we have all these, over 1 billion public tandem mass spectra here on the right. And so again, the most basic operation is we do a spectrum similarity, like a cosine similarity between our unknown spectrum versus all public mass spectrometry data on the right. And so we do this one at a time. And so in this previous example we showed you, this is kind of the first time, one of the first times that we enabled this. So there was no other way to do it, but it was, and people were happy to wait, tens of minutes to match a single spectrum against all this public data. Horrendously unacceptable. Just to give you an example, kind of in our first iteration of MAST, it would take us to query a single MSMS spectrum 15 minutes. Not great. Now you can imagine if you have 10,000 features where you want to ask this sort of question, where and when has it been seen before? If you're going to wait 15 minutes per molecule, you're going to be waiting a couple years to finish the query for your data set. So not particularly scalable from that aspect. And so, this is kind of an ongoing project, and one of the papers just came out recently. But MAST is slow, and how can we make it really fast? We won't go through the details, but the specific details. But the basic high-level idea is whenever you have your tandem mass spectrum, they have this property of sparsity. So you don't have masses at every single, you don't have peaks at every single mass, right? Most of the time, like your spectra is 99% empty. And so in our kind of slow way, we look at every single mass and we do the comparison, and we look at every single mass in all the public data. But if we recognize that we are querying with spectra that have mostly zeros for masses, we can exploit the sparsity. And so what this allows us to essentially do is ignore 99% of the data in our public data sets, which is great. So if we can ignore 99% of the data, that allows us to do the comparisons, but it allows us to do it, orders of magnitude faster. So this is a paper that we just published recently. It's called Blink, in collaboration with Ben, Nuno, and Ben Pullman. And we were able to increase the speed of our naive implementation about by 3,000-fold. So reasonable. And so we're able to transform something that took 15 minutes to something that takes now milliseconds. And so this really helps us scale whenever we want to repeat this particular procedure over your whole data set. And so this is available today. If you go to GNPS2, there's a little link to do MAST. And we cleverly call it FAST. Anyway, we thought it was funny. But definitely give it a try and let us know what you think. But again, this is kind of an ongoing thing that we're really trying to optimize, and it's definitely not perfect, but we hope that it moves the needle for everybody. And it's a much better workshop experience whenever it's near instant, as opposed to clicking go and waiting 15 minutes for everybody in the room. Okay, so with MAST, we were able, kind of in conclusion, we were able to take an entire tandem mass spectrum and ask, have we seen that same molecule in its entirety in all the public data? So once we created that, when we were working with Peter, it's kind of a, I don't know if you're familiar with the term. If you give a mouse a cookie, he'll want a glass of milk. So basically, you give him something, and everybody wants more, which is great. It kind of pushes us to be innovative. But one of the things that Peter, kind of flippantly asked, in a kind of excited way, is, now we can search all of these like these full molecules. But what if we wanted to look for specific classes of compounds, or even more, more broadly, specific patterns in the data? And so Peter, one question he asked is, can we find all carnitines in public data sets? Right? We have all this data out there, and they have tandem mass spectrum. Maybe how can we find all carnitines, right? And so I'm a computer scientist. One of the things that we can do is like, okay, I know something about carnitines. We know some specific rules about their fragmentation, specific masses and neutral losses in the tandem mass spectrum, we can write up a simple script that encodes specifically that, try to search all public mass spectrometry data and say, great, here they are, we're done. Unfortunately, or fortunately for us, again, so this is specific structural features of molecules yield specific and conserved patterns. So some of these include isotopic patterns, some of them are MS2 peaks and MS2 losses in the combination of all these things. But the bottom line is, whenever we could enable this once, the analytical chemists that we were working with, they're like, oh, great, okay, so how about let's change what we're looking for to different classes of compounds, or being even more specific about a particular class that they want to look for, so a particular type of compound or natural product that they want to start finding in the data. And so it quickly became a very intensive back and forth. Let's change this about what we want pattern that we want to look for. And as a computer person, I don't like to do any work. So we wanted to be able to create a raises the question, can we develop a universal computational solution to help chemists answer these questions so that I can sit back and not do anything? That's the dream, right? Instead of me writing any code for the community and collaborators, can I build a framework so they can express what they want to find themselves? And so we think the answer is yes. So one of the tools that we've been building, and it's available for use today if you want to try it out, is called the mass spec query language, and MassQL for short. And so there's several pillars that we want to build on for this particular tool. The first is that it's understandable. So for a lot of you all, it needs to be easy to read and write for chemists. A lot of you don't want to write big, big tools like in Python or whatever that take a lot of time to debug. We want it to be simple and succinct. It needs to be flexible, so it needs to be able to express all the patterns that you would want to actually search for and mass spec adjacent things that you might want to filter on, such as retention time and ion mobility. Also want it to be scalable, right? So if it searches one file, that's not super useful, but we want to be able to scale this to all public data sets. And if we can enable that, then if you want to search all the data that you personally have ever collected in your own lab, that's kind of a piece of cake if we can search everything that the whole community has deposited. And finally, we want it to be reusable, right? So we don't want these one-off scripts that are kind of dead ends. If you spent the time to figure out what you want to look for, you can share that with other collaborators within your own lab, with your students, postdocs, but also share it with the rest of the community so they can benefit from the knowledge that you put into this particular query. So those are kind of the 4 pillars. And so we're just going to go through a few of these and see how they manifest in the creation of the language. So first, to be understandable, we created these translation layers where you can, at the top is MassQL, and we translate to other languages, so it's a little bit more natural, especially during the learning phases. So here, for example, we want to find all MS2 data where there's an MS2 product P to 468, so we can see the translation along with it. And if we want to start adding other conditions, maybe we want to have 468 and 660 M over Z within this. And I actually didn't include this in the slides. So we show this going from MassQL into English. And again, it helps you learn from examples. But one of the very cool things that has come up over the past couple months, I'm sure you've all heard of it, is things like ChatGPT and these large language models really becoming pervasive. What's been really fun is that now you can write something in natural language and ask it to translate back into MassQL, and it can do it. And it's very impressive. It is hilariously impressive. But anyway, if you don't want to learn MassQL, you can just write it in English and then it'll write it for you. So that's kind of a side point. Again, so that's being understandable. Flexibility in terms of describing mass spec patterns. So these are, here are a few examples of certain things you can query for. It's not exhaustive, but on the top left here, if you want to look for MS2 spectra or MS1 spectra with specific peaks, you can express that. To the top right, you can say losses from precursor. there's a particular term for that, MS2NL, you can start looking for gaps between peaks. It doesn't have to be, you don't have to know what the peaks are, you just know that there's a neutral loss between them that is not, and they don't have to be the precursor, as well as enforcing relative peak intensities between a subset of the peaks that you're interested in. And so the nice part about this is you can mix and match any of these conditions that you actually want to search for. So if you want to look for a product ion and a neutral loss from precursor, you can combine those two things with these conjunctions. So just walking through one particular example, you've met Danny. And so this is some work that he had published, I believe probably in his PhD work. He was working with some natural product compounds. In this particular case, a family called albacidins. And so he knew that albacidins yielded distinctive fragmentation at 468 and 660 mMol/Z. So that's something he knew about this family of natural products. And so he could easily write a MassQL query and find a family of molecules within his own data, something that he had predominantly done manually by flipping through hundreds to thousands of tandem mass spectrum, which just kills me as a computer person. And so he was able to do this. And we created MassQL after he published his paper from 2017, but we looked back at the data. And we were able, with MassQL, very easily to find all the known compounds that he had originally published on kind of in a few minutes. So that's, pretty exciting to be able to, that's our positive control to be able to do that. But what was a little bit more exciting is we were able to apply MassQL and visualize here with a molecular network, and highlighted in blue here are the known albacidin analogs that Daniel had published back in 2017. But what we also revealed within this molecular network are in gray, which we think are putative new analogs of albacidin that Danny did not publish on. But we were able to very quickly, in a few minutes, kind of extract them out and organize them and create a hypothesis to say, okay, here are some new analogs. If you wanted to actually continue this work and discover more structural analogs, here they are. This is an area for prioritization and discovery that leverages his domain knowledge of this particular compound class and allows for discovery relatively quickly. So we thought that's one use case of this particular tool. And so the next point here is about scalability. And so we want to, really roll this up again, just like mass. We want to be able to scale this up to all public data that's out there and see if we can make use of it. And so one particular application that we'll highlight here is working with Nina Zhao, who's a postdoc at UCSD. And so she cares a lot about environmental chemistry. And so what she was looking for during her PhD work was a class of compounds called organophosphate esters. And so just a broad kind of overview of why they matter. They're used in flame retardants, and there's a large diversity. So there's hundreds of known analogs of organophosphate esters, and they're not particularly good for our health, human health, and they end up in our waterways. So it's good to at least understand how much diversity there is of these molecules and how big of a problem it potentially could be. And so what Nina knew about this particular compound, class of compounds, they generated a distinctive fragmentation at 98 mMol/Z. So she knew that, and so she was able to write very easily, again, it's not particularly complicated, is a query that looked for MS2 spectra with this particular fragment, and it had to have been a very high intensity. So that's something she knew about the fragmentation. And so what we're able to do, because we built out this whole ecosystem and infrastructure for MassQL, is throw in all public data from GNPS, Metabolite, Workbench, and Metabolites, and search these 1.1 billion spectra. To manually go through all this, not the most fun thing to do. But with MassQL, we were able to filter out this 1.1 billion down to about 330,000 MSMS spectra. That's still quite a large amount that exhibit this particular pattern. And so there's a lot of repetition. And so what we did was we collapsed identical and merged identical MSMS spectra to reduce the redundancy. So this yielded about a little under 3,000 unique tandem mass spectra, and we visualized them into families of similar fragmentation with molecular networking, something you all have learned a little bit about. And so this reduced the complexity even further by another order of magnitude. And Nina was able to start exploring this data that she was not able to explore previously, just because we couldn't create molecular networks of all public mass spec data before. And so what she was able to glean from the results from MassQL is that known organophosphate esters could explain about under 10% of the masses that we found here. But as she was coming through, she was able to discover new organophosphate esters that hadn't been described in her original publications in this data, because she just was not exhausted in that. And number two is she was able to discover some new organophosphate esters uniquely because we scaled the search out to all public mass spectrometry data, and these organophosphate esters did not actually appear in her own data sets. So it's kind of, she was more comprehensive of her own data, and we were more comprehensive because we could have used the totality of everybody's data and create a better catalog of putative organophosphate esters. So that was kind of one avenue that we think using all this public data could reveal the full diversity of the chemistry, or a more full picture of the diversity of chemistry that somebody may be looking for. And organophosphate esters is kind of one example of that. So the final pillar, again, we want to go through is reusability. How do we start sharing and reuse these queries that you might come up with? And so one thing that we've created, just as a small thing, is called the MassQL compendium. And so this is a curated list of MassQL queries that people can deposit, saying, hey, these are the queries that I used in my own lab for this particular purpose. So whether looking for peptidic natural products, specific features for, if you're doing a semi-target or a semi-targeted like lipid, looking for specific lipids in your assay, things like that. People have been depositing these, and you don't have to write queries from scratch, right? You can borrow from others. And we've also described a lot of the application of these queries in the supplemental information of a manuscript that is currently under review. And so not only is it good to be able to do, run MassQL at GNPS2, you can also run it on the command line. But kind of further is that we want to make it more universal within the community. And so you can imagine, because it's a language, right? So it's the mass spectrometry query language. We want everybody to be speaking a similar language when you want to look for these patterns. And what we've done is we've created software to enable that. So we created Python APIs and R APIs that are open source for people to use in their own software, and you can run it on the command line on your own computers and as a workflow on your own computers if you would like. But however, to make it more user-friendly, we've integrated it into a lot of the most popular open source and some of the commercial tools out there. So one that you probably more experienced now with is MZMine. So it's starting being supported in MZMine 3. And so the dream is that you could imagine writing a MassQL query in GNPS or GNPS2, applying it to your own data. That exact same query you can hand off to your collaborator or a friend in the field, and maybe they don't use GNPS, and that's okay. They may use MZMine, and they can plop it into MZMine and apply it to their own data, and you can expect the exact same behavior. So it's kind of a portable way to do analysis that is consistent. And so we started supporting in things like MZMine, Unideck for, this is actually for top-down data, MS-Dial, OpenMS. So again, these are really popular metabolomics and mass spectrometry suites. We support it in GNPS and the GNPS dashboard, as well as Bruker now supports it in the 2023 version of Metaboscape. So we're seeing some commercial interest. Anyway, so we're very excited that it's being adopted. So hopefully we can realize our dream. But also, if you want to contribute or you just want to use it, definitely reach out. And it's kind of all open source and isn't out there. So in conclusion, kind of all of these points is that GNPS2 is a new platform that we want to get out into the community and enhance resiliency and lower barriers for use of computational tools. And in that similar vein, MAST and MassQL are new tools that help you mine your and public data, but specifically it helps lower the barrier to entry for people to start interacting with all this public data out there and democratize kind of the analysis. And also the way we've architected these things, you can run them at many different sites, so it democratizes and creates resiliency in those particular tools. And a lot of these things are available and in beta today, so definitely try it out, and feel free to reach out to me in my lab, as well as anybody. Everybody here sitting in front of you knows everything already, so I'm not even necessary as part of this equation. But again, we want to make tools useful and open and collaborative. So definitely reach out. We love hearing from everybody. And if you want to contribute, seriously, anybody can do it. Enthusiasm is the biggest thing that's necessary. So, and I just want to acknowledge kind of collaborators as well as my own, my own little humble lab over at UC Riverside, as well as throughout the years. We've been very fortunate, or especially me, I've been very fortunate to have worked with hundreds of collaborators, and we've published good papers, and hopefully impactful papers. But what's really fun is just the community that we've built that's been supportive. And I'm, very grateful, especially when I was a humble, grad student. People in the community took a chance to use my tools, and that has really, I built a career out of it. So I got a job because of it, and so I'm really thankful, especially to a lot of the people kind of leading this summer school. So anyway, I definitely want to thank them, as well as funding from the NIH, the US NIH, the Joint Genome Institute, some gifts from Agilent Corporation, and my startup at UC Riverside. So happy to take any questions. I know I'm standing between you guys and beer and dinner, so don't want to keep you all too long.
Ming, for that great talk. I think we have time for questions. Microphone.
So there's one in the chat here. From Xinghui, are you considering the function once you plot a MassQL, or once you, you apply a MassQL query, can you download the molecular network of the feature list of compounds that have that specific fragment? So yeah, the answer is yes. So one of the new things that we're all about integration, right? So and being able to export, and you can do whatever the heck you want in other tools. And so one of the things that we can do in GNPS, on the GNPS2 side, especially with MassQL, is we can start visualizing entire molecular networks in the browser, which is, not the fanciest thing, but it is convenient. But we've also integrated that particular functionality with MassQL directly. And so earlier today, you guys created molecular networks, but you have to download this in the Cytoscape, which is, a really powerful piece of software, but it doesn't really know about mass spectrometry data. And so we've enabled this in the browser, so you can apply MassQL on top of a molecular network, and then it'll highlight everything, and then you can download that table, and you can work with it. If you work with it in Excel or anything like that, totally possible. So there's definitely reach out if you want to try this. Happy to show you all these things. One of the things is this. One thing we're really bad at, one thing that maybe we'll frame it the other way. One thing that we're very excited about is working with individual collaborators and say, we have this sort of need, right? And then we build kind of these features, because it's fun to build tools that are actually being used and useful. And we don't tell anybody about it. we're all busy. And then, so just one particular anecdote is Alan, John, you all met Alan. Whenever we were postdocs together at UCSD, there was a particular feature for creating histograms or something of molecular networks that I had implemented because I was having fun back in like 2015. You know, it's late at night. You're like, oh, it'd be fun to do this. And then like in 2019 or 2020, he's like, Ming, it would be great if we did this. I'm like, Alan, we did this. He's like, God damn it. I wasted so much time. Anyway, so it's probably good to ask first in case that we've already done it instead of wasting time. But it's just, we do a pretty bad job of advertising everything you do, or everything we can do in a lot of these platforms. So just kind of a small anecdote. Any other questions? Well, feel free to bother the people that are like, when you go out to dinner, to ask them questions. They know more than me about actually using these tools anyway. But one of the things that I have been hosting, but I kind of stopped because baby's crying and things like that. But I'm transitioning out of paternity leave soon. I host office hours every Tuesday morning at 9 a.m. At Pacific time. But that's a great time to email me, or to stop by office hours on Zoom if you want to ask interactive questions. Sometimes, my apologies, I get a ton of email, so I don't always respond timely, but here is kind of a dedicated time to answer questions about our tools and things like that. And I'm trying to get some of my friends that are more experimentally minded to join me at these things, so we can just at least hang out. So hopefully it won't just be me, and you'll get a broader panel of expertise, but we'll see how that all goes. But anyway, thank you all for sharing this time with me, and definitely feel free to reach out and to collaborate, or use the tools. We'd love to get feedback. So if you use the tools, especially in beta, happy to have you use it. But my soft request, and I'm trying to guilt you all, is you got to tell us good, bad, or ugly. That's my ask of you guys. So anyway, thank you again to you all and the organizers for having me. I hope the rest of the summer school is a success. So
Thank you, Ming. Hey, Ming, can we borrow 2 more minutes of your time?
Yeah. I'm going to take a nap right after this. So whatever. I don't have a pressing meeting.
There's a couple more questions in the chat. So you need a different account to log into GNPS2, right?
Yes. So it's a different. Yeah, they're new. It's kind of so. Oh my God, it's a thing. So we're not we are a very modest. So to give you an idea, so I'm a big computer nerd. So I've been building computer desktops for a long time, since I was 12 or 11. So I've always had a fascination with hardware. So we put together a very modest computational cluster in our server racks at Riverside. But the thing is, we have a finite budget, and anyway, small anecdote. I've been buying used server equipment off of Reddit, which has been so much fun. But anyway, I'm pretty frugal guy. They're rock solid, but the thing is, we just don't have a huge budget like UCSD had for petabyte scale storage. So we don't want to open it up to just have a free-for-all. So we're slowly ramping up, giving out accounts and figuring out management of resources and things like that, how much we can safely give out for free. So we're still figuring that out. But since you're at the summer school, email me, happy to make you an account. We're still in the early phases. We have just a few hundred users right now. So it's very manageable, and we're upgrading the servers for new compute and storage and things like that. But we're trying to grow slowly so that we don't run up against a hard wall and promise more than we can deliver. But you're at the summer school, so kind of friend of a friend kind of thing. So definitely reach out, and we can make you a new account. Hopefully it's easy to use, but it's definitely a work in progress.
Great, thanks, Ming. I think a couple questions for self-resolved in chat. So community's already answering each other's questions, which is good. I'm sure, what do we do now? Group work? We're done. Oh. So Ming actually is keeping us, actually I am now. So thanks again to Ming for presenting. Bye, Ming. Enjoy your sleep.
Okay, take care, everyone.